Thanks for coming so early in the morning. Thanks to the organizers for inviting me. I realized a few days ago that I spent exactly half my life at this point working on random KSAT, which was a really odd observation. And today, I think I'll be sitting in front of certain physicist colleagues and saying non-rigorous things. So that would also be hopefully a first. So anyhow, that's what I'll talk about. It's joint work with my student Kei Zhang. And the setting is a very familiar one. We have some large domain, which we can think of as just being the Cartesian product of variables with discrete domains. And we have some non-negative function that we would like to sum over the domain. So we just want to compute the so-called partition function, although I won't necessarily have some statistical physics or other model in place. It's just a generic function f. The only thing about it that's going to be important for us is that it's non-negative. So when you take this sum over the entire domain, there are no cancellations. That's the important part. And there are several reasons for which one may want to compute the partition function. Here are some of the standard ones. And you can perhaps think of the Stoch as proposing, actually, although the proposal is not quite mine, but think of it as a generic alternative to MCMC, whereby you try to compute the sum by optimization. Meaning you try to leverage other people's work on optimization to make the computation of this sum efficient. And when I say efficient, I mean efficient in practice. So in terms of the quality guarantee, the idea is we will give an estimate of the partition function, which is within a multiplicative factor. And we can make the multiplicative factor as small as we want. And we can make it be true with probability, which is exponentially big in the amount of work that we do. So for the rest of the talk, though, to simplify things, I will just assume that the domain is the binary cube. And I'm just going to talk about a 32 approximation of the partition function. In all the cases that are going to be of interest, the partition function is exponentially large in n. So a 32 approximation is like, log, an additive approximation. You just add a few bits. So just keep that in mind for the rest of the talk. And here's the general idea, and the general idea is not mine. So we're going to assume in a certain sense that P equals NP, and we will use that to try to do the counting. By which I mean we have some piece of software which for the domain of interest can actually determine an NP-complete problem, whether it is solvable or not, as is the case for example, for practical satisfiability instances. By which I mean there's lots of practical satisfiability instances which have tens or even 100,000 variables that people can solve in minutes, and they actually care about them. And for some of these instances, they also would like to count the number of satisfying assignments. So now the question is, can you leverage all the effort that they have put in building the satisfiability solver to do the counting? So the idea is we're going to repeat a bunch of times, where the number of times just has to do with the accuracy that we want. We're going to take a random subset of the cube, the size of which is going to be approximately 2 to the n minus I. And then we are going to determine the maximum of our function within this subset. So this is the part that acts like a black box. So again, there is the entire domain. There's our function living on on the domain. Then we're going to take a random subset, which I haven't said how we will specify it yet. And then we will ask our solver to find the maximum of the function over the domain, over the random subset. And if we get a bunch of such estimates, one for every I from 0 to n, then it's fairly straightforward to combine them and get an estimate of the partition function. And all this is known in its prior work. And the only contribution of what I will talk about is the idea of creating this random subset as the elements of an error-correcting code. So let me first walk you through through the general idea. So we'll start with a thought experiment, and we will assume that somehow we could sort the domain in terms of f value. So sigma 1 is the maximum value of, f of sigma 1 is the maximum value of f of sigma 2 is the second largest one, and so forth. And imagine that by some kind of miracle, we could get our hands on the n+1 numbers corresponding to f evaluated at sigma 2 to the I, So these things are increasing geometrically. So what we want is B0, B1, B2, B3, and so forth when n is 6. It's not hard to see that if we could get our hands on those numbers, then we could get a 2 approximation to the partition function. And you could replace 2 with 1 plus epsilon if the spacing became 1 plus epsilon instead of 2. So in particular, it's easy to get these two expressions, and as you can see, they only involve these numbers b sub I, and one is an upper bound on the partition function and one is a lower bound, and they differ just by a shift of the index of summation, so it's just a factor of 2. So this gives a 2 approximation. And the proof is sort of similar to Lebesgue integration. Rather than trying to integrate vertically, we integrate horizontally, and the factor of 2 observation is that the green line is an upper bound on the integral, the red line is a lower bound on the integral, and if you look at any horizontal slice, the ratio of what's under the red to what's under the green is at most a factor of a half. Okay, that's the proof. So we want to get our hands on those numbers, and it's easy to see that this is also relatively robust, by which I mean that if you don't get those numbers exactly, but you get an estimate for the ith such number, which is between b of I plus c and I minus c, then you get a 2 to the 2c plus 1 approximation. It's straightforward to do this. And by the way, all this line of work, I forgot to mention, has a sequence of papers by Ermon, Gomes, Sabarval, and Selvan over the last 5 years. So for example, if we instantiate c to be 2, in order to get a 32 approximation of the partition function, it suffices to find for each I between 0 and n an estimate of b sub I, which is between b sub I plus 2 and bi minus 2. So for example, for b3, we just need to find, if we can report any number in this interval, we're good. Are there any questions up to this point? Okay. So in order to come up with such an estimation, we're going to just use concentration of measure. So the entire point of the talk will be to construct some random variable x such that it is a reasonable estimator with probability at least a half. So generically, if x is any random variable such that it is with probability at least 1/2 plus delta less than an upper bound, then with probability at least 1/2 plus delta more than a lower bound, and we take several independent samples of it, and we return the median of those samples, then the median is going to be between the lower and the upper bound with exponentially high probability. So that's our plan. So we're going to come up with an estimator for each one of those BIs, then repeat a few times, and then just repeat and then just report the median of those. So our estimator, for now, again, I'm not yet telling you how we're going to take those random sets, but when we want to estimate b sub I, we're going to consider a random set which will have the property that it is uniform over the cube, and the probability that any particular element belongs in the random set is 2 to the minus I. So the size of our set is going to be 2 to the n minus I in expectation. And then our estimator for the function is going to be, for b sub I, is going to be the maximum of our function over the random set. So for example, if you think of f as being merely a 0-1 function, so that what you're really asking is, when I take this random subset I, are there still any solutions left? Are there still any places where f evaluates to 1? So it's a thinning of the original domain that we're going to do in a random manner. And we're going to thin down to the point where we expect that the number of solutions remaining is about 1, at least in expectation. So, for example, if we're aiming for b sub I, then this is what the picture looked like. So what we're hoping is that we will return something which is between b sub I minus 2 and b sub I plus 2. Okay? And in order for that to happen, we need that nothing above here survives, the thinning, and that at least something above here survives. And we have, we have an exponential number of candidates for this to happen. So, okay, one direction is super easy, and that's the probability that our estimator ends up being too big. And this is merely the probability that something that is too big survives. That's, in other words, the probability that our random set includes one of the top 2 to the I minus 2 biggest elements of the set. So just by taking the union bound, each of these is going to be in the random set with probability 2 to the minus I. There's 2 to the I minus 2 of them. And now we have probability 1/4 of overestimating. So remember, we just need probability that things don't go poorly with probability just slightly bigger than 1/2. So that's the easy direction. The real problem is avoiding underestimation, meaning that when we specify our random set, although in expectation its size is right, our random set is kind of clumpy. And by virtue of being kind of clumpy, it kind of hits the set of interest all at once and it wipes it out. Another way of saying it is, we don't want it to be the case that the expected size of the intersection is realized through a lottery phenomenon. We want it to be, we want to avoid that. So, more concretely, to avoid underestimation, what we need to be true is that although we do avoid all the elements up to 2 to the I minus 2, we do have some elements up to 2i plus 2. So in other words, if we let x sub I be the size of the intersection of our random set with the largest 2 to the I plus 2 element, we would like the size of this to be positive. And observe that the expectation of this is just 4. So we have two exponential size sets, at least for a generic I. The top 2 to the I plus 2 element. And then we have our random set, which was going to have size about 2 to the n minus I. We want them to intersect with probability at least 1/2, so we want intersection to happen often, while having expected intersection size 4. So in some sense, it doesn't look like a very promising situation, okay? So generically, you have the cube. Inside the cube, there is some set of size 2 to the alpha n for some alpha that you don't know, so it's an exponentially large set. You're going to take another exponentially large set, your random set. The size of your random set is such that the expected size of the intersection of the two sets is 4, literally 4 elements, and you want them to intersect with probability more than 1/2. Yet at the same time, you don't want the variance to be very big. So I think this highlights the idea that we would like the random set that we have to not be clumpy inside the cube, but instead look like some kind of a random mist that somehow pierces the cube uniformly everywhere. And at the same time, well, before I get to this, let me just sort of recap this in math. So we want to design a random set such that for uniformly every element of the cube, the probability that it belongs in the set is 2 to the minus I. This set should have a simple description. Remember that ultimately we're supposed to optimize over that set, so we should certainly be able to describe it efficiently. And then if you take any fixed subset of the cube, the variance of the intersection between our random set and S, a set S for which we know nothing, we don't know anything about the geometry of S, we would like the variance of this to be small. So it turns out that to minimize the variance, it turns out that the quantity that you need to control is the sum over all distinct elements of the unknown set S of the conditional probability that sigma prime belongs in our random set, given that sigma belongs in our random set. So there is a set S, you take any specific element in it, and then you say, okay, now I reveal to you that my random set selected this. What does this imply from the probability that some other element of the set sigma prime has also been selected? And given that we know nothing about the geometry of the set, a very sensible goal is to say that, well, ideally I would like you to say nothing about it. So we would like to have pairwise independence. So this is, in some sense, the golden standard, and if we can achieve this, we're super happy. Now, on the other hand, the idea that we have pairwise independence is not obviously easily compatible with the idea that the set R is easy to describe. By which I mean, this is supposed to be a set which is on one hand easy to describe, on the other hand it must have the property that if I tell you that something is in the random set, then the probability that something else is in the random set is the same whether that something else has Hamming distance 1 or has Hamming distance n over 2. That's what it means to have pairwise independence. Okay? So the characteristic function of this set must be really, really unwieldy. In any case, as many of you have probably already figured out, this is something that we already know how to do using so-called linear error correcting codes. So the idea is that we're going to take our random set R to be the set of solutions to a system of linear equations modulo 2. So it's going to be the elements of the cube that solve A times sigma equals B, where both A and B are uniformly random 0, 1. So every element of A is 0 or 1, each with probability 1/2 and independently. And every element of B is 0 or 1 with probability 1/2 independently. And the first thing to observe is that the probability that any particular sigma solves a system of linear equations is indeed what we want it to be, even if we don't impose any constraint on the matrix A. So for any matrix A, even if this is deterministic or the all zeros matrix, the probability that you match B just depends on the randomness of B. Because after you take this product, you have some fixed vector that's supposed to match this random vector. Well, the entries of these are 0, 1 with probability 1/2, so that probability is readily 1/2 API. So we already get the first part that we want. For pairwise independence, the proof is not significantly more complicated. Observe that the probability that both sigma and sigma prime are elements of the solution set is the probability that basically one of them, you can think of them as sigma solves the system, and then the product of sigma prime with A is the same as that of sigma, and then you can postpone in your decision making, in your choice of B, you can postpone this, and then you can just focus on whether this will happen first or not. So this shows that these two events are independent. And now to estimate the probability that A of sigma prime minus sigma is equals to 0, given that sigma prime and sigma are distinct, we can look at the vector of their difference, and you can fix any particular bit that you like. There's at least one. Observe that the only things that matter in A are the corresponding columns with which you're going to take the inner product. So now you can determine the randomness in all of those columns except for one. Okay? And you will have a vector here, the parity of which, whether it's going to be 0 or not, will now simply depend on finally determining each one of those random variables. So you can think of it as a deferred decisions proof of the fact. First fix all other relevant columns, hold one out, and then observe that 2 to the minus I will do the trick. So we get what we want. So we do have pairwise independence, and in a certain sense, we're done. Okay? So we can say define the random set sub I. In other words, when you want a subset of size 2 to the n minus I of the cube, that is really like a superfine mist inside the cube. Just take I random parity constraints. So form this matrix where each equation in the matrix has about n over 2 variables, because you're flipping a coin that is 50-50 for each entry of the matrix. And then in order to estimate B sub I, simply maximize F subject to these constraints. So that is the original proposal prior to this work. Is it clear? Perhaps? Okay. So the math works out, but reality doesn't. So if you try to do this, the results are not good unless you go to anything that is above a toy problem. So here's an example where you take a 10 by 10 ferromagnetic Ising grid, and we set the coupling strength at the external fields so that it is near criticality, by which I mean that you have a roughly equal contribution from all states at different energy levels. And what this plot shows is the following. The vertical axis is the value of the maximum in logarithmic scale, and the horizontal axis is the number of constraints that we have added. And what happens is, accept for a moment by fiat that green is pretty much the correct answer. And moreover, observe that what I mentioned earlier about criticality corresponds to the fact that there is contribution from pretty much every distance scale. So this is just an arbitrary line to guide your eye at 100 minus I. So if we add a few parity constraints, then we are tracking the partition function very well. But after you add something like 15 parity constraints, then your solver dies. And the best solution that it can find is far, far worse than reality. And then it keeps track a little bit again if you near the very, very end. Dense parity is what I have been saying so far. So this is the dense parity equations are the equations in which we flip a fair coin for every entry of the matrix. So a typical equation has n over 2. But it turns out that if you naively attempt to sparsify this matrix by saying set every entry to 1 with probability p, where p is some number less than 1/2, you also don't get good results. So, pardon?
What was the solver here?
We tried Cplex, but we've also tried different satisfiability solvers. We've tried local search. Pretty much nothing works. And the reason that nothing works in some sense makes a lot of sense. Okay, you have your constraint satisfaction problem or your easing model, meaning that each of the factors is highly local. It entails a very small number of variables. That's good. And then what do? You throw in constraints that have n over 2 variables each, okay, where you want n to be something non-trivial. So it would be nice if n, for example, was at least 1,000. And each of these constraints is a parity constraint, which means if it's not happy, you have 500 choices of which variable to flip to make it happy, right? By virtue of being a parity constraint, any change of any variable will actually satisfy this. So from the point of view of the solver, there's absolutely no guidance on how to proceed in the search. The branching factor is immense. So it has long been understood that it would be nice to achieve pretty much the same effect by using short parity constraints, except, like I said, if you do it naively by simply sparsifying the matrix A, it doesn't work. You get very, very bad results. So the contribution that we made was the realization, well, we made two, I guess. Let me first talk about this one. The first one is we're going to exploit the fact that these are random linear codes as opposed to just good codes, which means that we can alternatively express this random set, this subset of the cube that forms the code words, simply as sort of the up projection of a lower dimensional set into the cube through an explicit matrix G. So now I'm saying, okay, I have a subcube. Its dimension is going to be n to the minus I. So the code words are just take the entire subcube and filter it through this matrix, and you get your code words. The result of which is that instead of solving the constrained optimization problem, maximize f over the entire original cube subject to solving the CSP, by the linearity of the constraints, we can rewrite it as maximize an unconstrained optimization problem over a lower dimensional cube, where now what you maximize is f of x passed through the generator matrix. So one part of this story is positive, meaning that for the interesting values of I, the size of the domain has shrunk by an exponential amount. The downside is that now your function f has become a black box. So it used to be that in most cases you have a syntactic representation of f, like f is a satisfiability formula, or it's an easing model. Now you basically say, okay, here's my x. What code word does this correspond to? Please tell me what's the value of f there. So you are directly accessing faraway points in the higher space. So you can say that perhaps any sort of nice continuity properties that you might have for f in the original domain are kind of gone. Nevertheless, for problems for which you did not exploit the syntactic representation of f, which is pretty much whenever you use any kind of randomized local search, this is irrelevant. So if you were using randomized local search in the first place, you were already using a black box. so it doesn't really matter. And it works remarkably well. So in fact, this is how we actually got the answer for this particular model. So the first claim is, if you're basically doing maximum likelihood estimation by solving some kind of optimization problem through a stochastic random walk, you can pretty much use that code as is, and with a little bit of overhead be able to compute the partition function.
So G you took IID.
Yes, that's right. That's right. That's right. G is the, yes, that's right. Okay. So this is a case in which we don't say anything about sparsity. Okay, so we just use the nice statistical properties of the original final ensemble. And the downside is, like I said, that now F becomes a black box. So that was the first contribution. And it works well for problems in which you proceed by randomized local search. In the second contribution, we realized that, well, for certain problems, for example, for satisfiability, the reason that people are able to get to the point where they can solve problems with 100,000 variables is because they put a tremendous amount of effort into engineering that exploits the syntactic representation of your formula. So for example, they will try to find a good embedding of the formula, all sorts of tricks. And if you go with the route I presented earlier, all this is gone. So you would like to maintain the syntactic representation. And then the idea is to use low density parity check codes. And for the probably very few of you who have never seen those before, let me just explain what the main idea is in using these codes. So this is my matrix A. I have n columns and I rows, exactly like before. And I want most of them to be zeros, so that the additive of my constraints, so that each of the equations has few variables, so that when the equation is unhappy, in order to fix it, the branching factor in the search is small. So in the original ensemble, everything was blue with probability 1/2. I could have made everything blue with probability p. And like I told you, that doesn't work. So I'm going to do now something which is only slightly more intelligent than this. I will maintain the sparsity, but I will additionally require a lower bound on the number of blues in each column. So specifically, I will require that every column has at least 3 blues. And here's what happens. Imagine, for example, that I have some solution out here, and then I go and I flip a single bit. So I used to have a code word. I flip a single bit, as a result of which now each of the equations in which this bit participates is violated. It's a parity equation. As soon as you change a single bit, it has to be violated. So now, if I want to fix this without simply just going back to where I was, I can try to change a different bit. And let's say if I change this bit, I now have the fact that this equation is fixed because there are 2 things that have been changed. And this equation also got fixed. This one didn't get fixed, but moreover, I also introduced a new mistake. There's another violated equation. And then I can do it again. And because this is a talk, it works out beautifully, and at cycle of length 3, everything gets fixed. Right? So this is a code word at distance 3 from my original code word. Okay? The point is, though, that if I insist that every column of the matrix has at least 3 blues, there are not going to be any such cycles. The idea is, as soon as you change a variable, that variable participates by virtue of having degree 3 in 3 constraints. In each of these constraints, you have to now change something. And now that you've changed it, you still have 2 new constraints that just got violated. So basically, you get an explosive branching process of equations as soon as you change a single bit. And this is what makes it a good error-correcting code. So you change a single bit, and then the next closest code word is very far away, at least typically. I mean, there could be exceptions. But by and large, you get an explosive branching process for a long time before the cycles begin to close and you start getting phenomena like this. So just by changing so you can think of this in the original formulation. We had the balls and bins experiment. This is again a balls and bins experiment. The only requirement is that every bin gets at least 3 balls. It's exactly the same. Nothing else changed. So by doing this, it turns out that things get dramatically better. And solver is happy, because the typical constraint now has maybe 4, 5, 6, 7 variables, something that it can deal with. I mean, clauses, for example, often have that length. Yet at the same time, we have, by virtue of having an error correcting code, we have a set that still has this mistiness property that I talked about earlier, that manages to keep the variance of the intersection small. So concretely, this is a little bit of a cartoon, but not entirely. So what this plot shows is the conditional probability that sigma prime is a code word given that sigma is a code word. That's the vertical axis. And the horizontal axis is the distance of sigma prime from sigma, normalized by divided by n. So in the ideal ensemble, the one that has pairwise independence corresponds to this horizontal red line, where that probability is completely independent of the distance between sigma and sigma prime. So this is what we're aiming for. If, on the other hand, you take the original dense ensemble and you merely try to sparsify it, you get this really nasty tail back here. This is a huge bump. And this speaks precisely to the fact that you don't have an error correcting code, so you're going to have pairs of elements that are very close to each other. You're going to have clumps. In contrast, we use a specific LDPC construction, but it doesn't really matter. By using a low density parity check code, as I described, you get something which is like this. You get the green line. And the green line, it has a few aberrations, and dealing with those is sort of non-trivial. But for the most part, it tracks the red line exceptionally well. And in fact, the fact that it boils down to 0 here and here is a good thing. It's not a bad thing. It even further suppresses the variance. The variance of the random variable. And this is a picture which is actually by explicit enumeration of counting all the code words and reporting them for relatively small n. I think maybe n is either 32 or 40 for this example. And you see that you already get fairly close to the limiting behavior. And I forgot to say that the vertical axis is logarithmic. So that's why they work, because you manage to track the conditional probability that you get from long equations almost perfectly by using equations that are far shorter, by being clever about how you construct the equations. And I'll just talk a little bit about the computational complexity aspect. So if you think of your original solver is forgetting the additional constraints that we put in, is moving around in some kind of energy landscape and is trying to find, let's say, a minimum of your function. Let's say that instead of max, it's a min. I just flip it around. So, okay, it's doing its thing. And remember that our assumption is that that's something that your solver can already do reasonably well for the domain of interest. Because if you can't even maximize the function, then hoping to estimate the partition function is completely hopeless. So this is what your original solver is doing. And now what we're going to do is we're going to superimpose on this the Hamiltonian that corresponds to our system of linear equations. So what this picture is supposed to represent is you think of the 2 dimensions as the binary cube. The 3rd dimension is the value of the function you're looking for a minimum. So now I'm going to take this picture and I'm going to add to it, at least in the logarithmic domain, the function which has the same domain and simply counts the number of violated equations in my system. And then what I'm asking for is to find, let's say, an area where this function is 0, and then we can also always scale this so that we're looking for a 0. So we're looking for a joint 0 of the new energy landscape. So what we would like to achieve is that the energy landscape that results after we morph this one is not much harder for the solver. If we were using the dense ensemble, the one that I talked about originally, well, that's terrible because it's incredibly spiky. On the other hand, the whole point, one could say almost, of modern coding theory is to try to create energy functions, energy landscapes for error correcting codes which have the property that they kind of look like this. So I would like to argue that this looks very much like a modern error correcting code in the following sense. So again, 2 dimensions correspond to the binary cube. Third dimension corresponds to the number of violated equations. And the bottom of each one of those regions corresponds to a code word. So when you want to transmit information, you select the code word that you want to send. You can think of it as a little ball. You place it at the bottom of this basin. That's the perfect code word. Then you ship it through the channel. The channel perturbs it, but hopefully by not too much. So the channel perturbs it so that you don't land out here. You still land sufficiently close to the original that a naive algorithm, something like gradient descent, which is mostly what BP decoding does, will bring you back down. Does that make sense? So the idea is that superimposing such a Hamiltonian to the Hamiltonian of the original problem doesn't make the life of the solver significantly harder. Because practically what happens is most of the time the linear equations to be solved have nothing to say. This is a cartoon in the sense that actually these areas are far larger than what is depicted here. But most of the time they have nothing to say. And at some point they just kick in and say, okay, you know what, forget it. If we're here, then the only reasonable place to go is to go down. And then it takes over. So your original solver either solves the original problem at any given moment or is doing error correction decoding. And in some sense, both of these problems are supposed to be easy. The original problem is supposed to be easy by assumption. The second problem is easy because decoding is easy because we've decided the codes to be like this. And so the end result is that when we use low-density ParityCheck codes, we can scale to problems with thousands of variables. And in particular, the resulting running time, the running time of maximizing the functions subject to the additional constraints and finding a good lower bound for the maximum is almost transparent. So the running time for, let's say, when you want to prove that a formula is satisfiable subject to additional parity constraints is comparable to the running time of finding a satisfying assignment without any such additional constraints. Now, the unsatisfiability side is much, much harder, partly because proving unsatisfiability is generically hard. But one thing that we can say is that in all problems where ground truth is known, we get exactly the same accuracy as by using long parity constraints, and the method can be quite a lot faster. I'll just close with giving some plots. So these are experimental results. And each point that you see represents one CNF formula. This is a collection of about 200 CNF formulas that people use to measure the performance of satisfiability counting solvers. And they're sorted. So this one is easier to explain. This is time. And this is the logarithm base 2 of the amount of time it takes when we use long XORs versus using long LDPC to provide the same answer. And you can see that the speed up can be from a factor of 4 or factor of 32, 256, or even to 1,000. And in some sense, I think this will actually continue going for a long time. The only problem is that we don't have solver formulas for which we know the ground truth that are big enough. So we do get meaningful results for formulas that are practically interesting. This plot is, I have to spend a little bit more time to explain. Like I said, we can get lower bounds on the partition function. So this is what this little hat is. And this is the ratio between the lower bound that we get versus the lower bound that a solver can deliver when it is fed with long XORs. So we would like this quantity to be big. We want our lower bound to be significantly better. So then you first take one logarithm. So this, you can interpret the inner logarithm as telling you how many more parity constraints you can add, how many powers of 2 our lower bound is than the 1 by XOR. And then the second logarithm is so that it fits in the plot. So the number of additional constraints that we can add can be as high as 2 to the 10. So this is like a factor of 2 to the 1,024 times better lower bound.
So what is how do you construct the lower bound?
So the lower bound is given whenever you find a satisfying assignment. In other words, if you give me a formula and I can add a bunch of constraints, I constraints, each of which kills half satisfying assignments. And in spite of adding I constraints, I can still find a satisfying assignment. This proves that the form proves in the probabilistic sense that the formula has at least 2 to the I assignments, right? So the point is, by adding short constraints, we can allow the solver to find solutions and survive far, far, far deeper than by adding long constraints. If you add long constraints after 10 or 15 constraints, the solver just gives up. So, and that's it. Thank you.
Great questions. Yes.
About the problem of generating big benchmarks where you know the number of solutions, I was wondering if one could take a simpler problem, like for instance Zorsat, where you know the rank, and convert it to a CNF.
Yes. Or even NAE, for example, for which we have very nice bounds for not all equal, or which is even closer in some sense to what people care about. The only problem with these benchmarks, right, is the fact that I'll say it, it's a mean field model. So, so there is no geometry, and the practitioners don't care as much about it.
But in the encoding, you will create some gadget and some structures in it. So.
But why would I need to do that? I can take a random NAE formula, yes, and use that. So our main problem was to see if we can scale with formulas that people actually care about, like 10, 20,000 variables from some kind of a VLSI circuit, and see when you add those additional constraints, how much pain do you induce on the solver? That was the main thing. And by the way, these results are by treating the solver as a black box. So although I showed it in the slides, currently the code that we have doesn't exploit the fact that you know what the energy landscape looks like for an error-correcting code. So what we're working on now is also additionally exploiting this explicitly in the design of the optimization.
We had a talk here in an earlier workshop by Moshe Varda, who was describing some kind of similar ideas.
It's very similar.
So how does your work compare with that?
So you saw this this comparison where it was log-log. So that was their lower bound. So they use still long XORs. So
They claim that it works very well.
no comment.
Okay.
Well, okay, let me at least make one comment. In many of those practical problems, there exists a very small set of variables that actually determine what's going on. So if you can identify those, which is a completely orthogonal problem, then you have a much easier problem to deal with. And to that problem, you can apply long XORs. The problem is that identifying those variables that literally lock what is going on can be quite tricky. So when they say that it works on problems that are very, very big, what they mean to say is that they work on problems that are very, very big, which are rendered very, very small by being able to identify those variables. We're using our code. Literally, our first experiment is take their code, change nothing other than the error-correcting code that you use. Just change the matrix. That was the only thing. And then you get a speed up of a factor of 1,000 on realistic formulas.
Other questions? No. All right, good. We'll see you in 10:30.